right, so vectors. If it just has a magnitude such as distance or speed, we call that a scalar. But if it also has a direction with that, like displacement or velocity, then we call it a vector. So what we're looking for, does it have a direction and does it have a magnitude? So here's some. I want you to just brainstorm through them. I can go back. Brainstorm through these ones and figure out if they have a direction and a measurement, a magnitude, or if it's just got one of those things. Let's see how you did. Outside temperature is 15 degrees. That is a scalar. 60 kilometers an hour, but it doesn't tell us which direction. This one says due north, so we do have the direction and its speed. Wind is blowing from the south. That is a vector as well. Or neither here because we don't know the speed, sorry. Upwards tells us the direction. 10 newtons tells us the magnitude, so that is a vector. A mass of 5 kilograms is just a scalar. Car is speeding eastwards is neither, because we don't know how fast. Bulldozer moves a rock eastward 15 meters. And this one is, because we know that a direction is down. All right. So how do we draw vectors? Draw them with a straight line and an arrowhead. So notice that arrowhead doesn't have to be right at the end. That arrowhead can be in the middle of that vector right there. A position vector always starts from the origin and goes to some coordinate, x comma y. And you can write that as a column vector. So we're going to find out that we're going to write a lot of things as column vectors. We always put x on the top and y underneath. Now you might think back to the labs. You saw this a little bit in one of the labs when you had to do a translation and it gave you a column vector for the translation. And then the top coordinate you learned was how much you had to move it left and right, and the bottom one is how much it needed to be moved up and down. So that's a place where vectors can be put into other units, because we've seen it for translations in our transformations unit. So here we've got a vector OA. It is a position vector because it starts from the origin. We can write it as a column vector because it ends at the point 6, 3. You'd put the 6 on top and the 3 underneath. As far as writing vectors, you'll see in your textbook that they often write vectors with a bold letter, so bold letter A. Now when you're writing your own notes, that's kind of hard. I guess you could go over the A a bunch of times and make it thicker or bolder. But what we often do is we often underline it to show that it's a vector, or you can also write it with an arrow over top to show that it's a vector. I remember in university, I always used to write them like this. I don't know if that was I was too lazy to put the other arrowhead on, or if we were actually taught that. I can't remember. So again, just like you've seen everywhere else, your x represents how much you move horizontally, your y represents how much you move vertically. So here we have the points 1, 2, and 3, 6. So we can draw them, and as we draw them, we can sort of indicate how much we've gone left and how much we've gone right if we were moving from A to B. This is the idea of vectors. Vectors is concerned about where you start and where you end and looking at those things. So if we start at A and end at B, we've gone 2 units to the right and then 4 units up, and we could write that as a column vector 2, 4. So what vectors do is it gives us an idea, basically the same idea as slope. Can you see how the slope is sort of built into this? The slope of that line would be 4 over 2, or 2 over 1. But when we write it as a column vector, we have 2 over 4. So we sort of have the slope, but the other way around. And a vector is really concerned about where you start and where you end up. So the fact that it tells you go over 2 and then up 4, you end up in the same place as if you had gone along that diagonal line. Of course, notice if you wanted to go from B to A, it'd be exactly the opposite, right? You could go down 4 and over 2, but we always put the x on the top. Or you could have, if you want to do your x direction first, down over 2, down 4, and you'd still have that -2, -4. So we find out that an opposite vector is the same vector just in the opposite direction. Some other definitions, we have unit vectors. Unit vectors have a length of 1. So any point on your unit circle could make a unit vector. We have some standard vectors. We have the vector I and the vector j. And all that means is 1 unit to the right or 1 unit up. So now we can write any regular vector, and here's our vector from before, 2, 4. We could write that in terms of I and j. Well, we would go 2 units to the right and 4 units up. Well, 2 units to the right is 2 of these I vectors, and 4 units up would be 4 of those j vectors, so we can write it as 2I plus 4j. And we call that the unit vector form. Again, you either, when you write it in your notes, you either have to put an arrows over top the I and the j to show that they're vectors, or underline them. I think I prefer the arrows over top. Makes me think of a vector. Instead of underlining, then I might think it's important to study for the final exam. So, there is a bunch of vectors. What I'd like you to do is write them in column vector form and also write them in the unit vector form, and we'll put the answers up in a second. Done? Because if you get the first couple, I'm sure you can get the rest. Did you get 3, 2 as the column vector, and then 3I plus 2j? So it's important that you look at the arrowheads, because you have a starting point and an ending point based on that arrowhead. So for vector C, it's 2, -4, which is 2I minus 4j. There's vector B, and finally vector D. So now we can do the same thing in 3 dimensions, but we add another axis, the z-axis. So we have our unit vectors I, j, and we add another one, k. And again, as far as writing them, x, y, and then z. So what you have to kind of imagine is you've taken a piece of paper. Okay? Let's take out a scrap piece of paper here. And you write your x and y axes on that scrap piece of paper just like you have before, right? And you put that on a table and you add another one that's straight up and down. Now when you're drawing it in 3 dimensions, what you have to do is you have to start with your x and y axes and kind of imagine you've put it down on a piece of paper so it kind of looks like this. Can you still imagine this is a right angle there even though it doesn't look like it? But if we're doing it in 3 dimensions and you were looking at it on a table, it might look like that. And then you just add your z-axis to that. And so there's a right angle between the x and the z, which you can see automatically, but there's also a right angle between the y and the z as well. Okay? So now you imagine you have some point in space. That point in space is gone -9, here would be -9 in the x direction, 3 positive in the y direction. So what would happen is if you drew just -9, 3, can you see that that point would be right there on your piece of paper that's been laid down flat? And so this angle that you go here is still 90 degrees, and it's the same as you make your axes. And then you've gone up 4 in the z direction. So let's say 4 is there. That's this distance. So I need to go up that same distance there. And now I have my vector -9, 3, 4. Maybe 5 years from now they'll have 3D smartboards and I'll be able to just bring it out in front and draw things like in 3 dimensionals in front of you. Maybe they already have that and I just can't afford it. So how long a vector is, the length of the vector, is its magnitude. And we write that with absolute value bars around it. Because if you think about absolute value bars, the first time you were taught it, well, you might have forgotten what it meant and just remembered that absolute value of 5 was 5, absolute value of -3 was 3. It's whatever the number is inside, you just make it positive. But if we go back to the definition of what the absolute value was, it was how far something was away from 0. It was its distance. So if you think, how far is 5 away from 0 on your number line? It was 5. And how far was -3 away from 0 on your number line? Its distance was 3. So when we talk about the magnitude or the modulus of a vector, we use that same notation because it makes sense. It's asking how far from its starting point is the end. And we can figure that out by using the Pythagorean theorem. A squared plus b squared equals c squared. And what's really cool, and we'll see it in our notes in a bit, but you can do the same thing with 3 dimensions, okay? You would have to do, first of all, if I wanted to figure out how long this vector v was, I could do a squared plus b squared equals c squared and do this length right here. And then once I have that length, I make another right angle triangle and I could do a squared plus b squared equals c squared again. What's really neat about doing that is that the formula just becomes the square root of a squared plus b squared plus c squared. And you need to fill this out in pen. And this is what it looks like in your formula booklet. So your first question is at the bottom there. Try it on your own. Square root of 106. Okay, notation-wise, make sure that when you put in -9 that you had brackets around it. You just didn't just write -9 squared, because technically that would just mean the 9 is squared times by a negative afterwards. Here's 3 more. All right, whether you're done or not, you can check. Maybe you knew that this one was 5 even before you figured it out, because it was a 3, 4, 5 triangle. Second one is square root of 75, but you could simplify that to 5 root 3. And here we have a pretty one, because you have 3 in numbers and it comes out to a nice number. I mean, the 3, 4, 5, that's called a Pythagorean triplet. I don't know if this is called a Pythagorean quadruplet, but maybe we'll call it that because it sounds nice. So now, before, if you remembered the 3, 4, 5 as an important triangle, now in 3 dimensions you can remember the 6, 3, 2. Is that the first one? Now you've got some work to do. Okay. So now, how can we ask the same kind of question in different ways? Well, we could give you your vector in unit vector form and have one of them unknown and tell you the magnitude of that vector and get you to solve for A. So you would set everything up the same way, and now you just have to solve for A. Well, how do you get rid of that square root? Square both sides, get A by itself. And when you square root something, you have to remember it could be plus or minus. So key concept number 1 of vectors is how do you find their lengths? And that's just by doing a squared plus b squared equals c squared, or in 3 dimensions, a squared plus b squared plus c squared equals d squared. So a unit vector can be in any direction, not just in the axes. And here's our notation for the unit vector. And again, if you're writing it yourself, you could underline it to show that it, or you could attempt to bold it. So here, we have this vector, which we already figured out before had a length of 7. So if we wanted to write the unit vector in the same direction, we would want it to be in the same direction as 6, 3, and 6, negative 3, and 2, but be 1/7 of the length. So one way that we could write that, well, first of all, we figured out that its length is 7. One way that we could write it is just by writing the vector that we had to start with and put a 1/7 out in front. Because if this has a length of 7, by putting that 1/7 out in front, we would make it a length of 1. So one way that you could write it is with the 1/7 out in front. Another way that you could write it is that 1/7 could get distributed to each coordinate, or each x, y, and z. And then the last way that you could write it is with your unit vectors. So there's a bunch of different ways that you could write your answer. Off to the side there, we wrote down what the formula for a unit vector is. So whatever the length of your vector is, you just have to divide by that and multiply that by the vector you started with. I personally, of all these forms, that one's my favorite. I like to see my original vector and just have a scalar out in front showing that I've multiplied it by 1/7. It also means that for some of the math that we're going to do later for vectors, we're using more whole numbers rather than fractions, which can end up being nicer to do. So this is our second key concept, is finding a unit vector. And we need to know our first key concept was finding the length. And all we have to do to find our unit vector is take the length of our vector and divide by that and multiply it by the vector that we had to start with. That will give us a vector that has a length of 1. Now, if you were to take this and do a squared plus b squared equals c squared, what you would notice is you'd have fractions. And all those fractions, when you square them, would have 49 on the bottom, right? And we already know that the length of 6 negative 3, 2 was 7, and you would have 49 in the top of that square root as well. And then, of course, 49 divided by 49 is 1, and when you square root that, you get 1 as well. So there's 2 here for you to try. Actually, you can try the last 2 examples. I'll put the answers up in a bit. So you can check how you did on that first one. Find the length to be square root of 29. Then you can write it, your unit vector is 1 over the square root of 29 times by the vector you started with, 5, negative 2. You could also have written it in unit vector form. So again, in 3 dimensions, you find out the length. The length is a square root of 61. Then you can write your unit vector like that, or you can write it with the I, J, and the K. No problems. So now to imagine this one. We have a vector in 3-dimensional space that goes 5 in the positive x direction, then negative 3 in the y direction, and finally 2 up in the z direction. And so we have a vector in a certain direction. And we want to find another vector that goes in that same direction, but its length is only the square root of 7. So the idea here is we can use our unit vector. First of all, we can find out that our vector v here has a length that's the square root of 38. So our vector v is longer than the vector that we want. We want our vector to just be the square root of 7. Now, these numbers were chosen on purpose so that it wasn't just like, oh, I can see easily how to do this. But what we can do is we can find our unit vector easily. That would have a length of 1. So now if we want a vector to have a length of the square root of 7, all we would need to do is multiply by the square root of 7. Again, you could write it like this, or it might have been nicer to have that unit vector written out in front like we had before. That would be the same thing. So the idea being, if we can find our unit vector, and that has a length of 1, then if we want a different length in that same direction, we just have to multiply by that length that we want. So if you wanted the length to be 3 units long, well, we find our unit vector and multiply by 3. If you wanted a vector to be a length of 10 units long, find your unit vector and multiply by 10. So if you want more practice questions, there's some listed at the bottom of the page there.